stuff which is already there where you can just do the I mean you can just uh, calculate up till a certain power, so then it's more convenient. Anyway, I'll try this. So this is regarding the first question of the homework. Okay, so we are in lecture 23. My handwriting seems to deteriorate. Um, so what were we doing? We were doing symmetric functions, and lambda k xn was lambda k x1 to xn. And what we essentially did was we gave a map from this guy to c raised to the power pnk, where pnk is the set of partitions. Uh, so lambda is a set of partitions of k. With the less than equal to n parts. And we showed, and this map basically took this guy from this to the coefficient of lambda and f, right? And we showed, I mean, this is a linear map. We showed this, and we showed it in a very different language. And what we found was that m lambda is basically the elementary basis. So remember, in linear algebra, you have this basis element, all zeros and one in the ith place. Essentially, this is what m lambda is. Everything except for the lambda position, you have this. So what we showed was that this map is a, so essentially we showed that this map is an isomorphism. And if it's an isomorphism, then so this is in a different language. This is what we do. So so this is important to understand, that m lambda, why are we starting with the monomial symmetric function, a monomial symmetric this thing? This is lambda. Now the other aspect I have sort of glossed over, that you can essentially work in a finite number of variables. It doesn't matter. So that is somewhat complicated. It's better if somebody better in algebra explains it to you at a later stage. But right now, just understand that the basic idea is that instead of infinite variables, you can check things for finite variables. You should just understand this, what it means. Okay, so the next item we want to consider today is elementary symmetric functions. And what they are is EKN is defined as so you take x I1, x I2, so on up till x Ik, so k of them, and I1 strictly less than I2, strictly less than I3, strictly less than Ik. So distinct guys. So for example, E1n is same as xi, so x1 up till xn. And again, depending on context, we can work only in finite number of variables. Okay. E2n will be things like x1, x2 plus x1, x3 plus so on. So xi, xj for I less than j. Okay. Um, for example, E2 of x1, x2, well, this is xn. X3 will be uh, x1, x2 plus x1, x3 plus x2, x3. And again, note that if k is bigger than n, then ek of xn is going to be 0. And the theorem here is any f belonging to lambda k, well, even lambda xn can be written neatly as a polynomial in E1 xn, E2 xn, and so on up to En xn. Okay, so what are we saying? We are saying that m lambda, we know that any polynomial f can be written in terms of lambdas, m lambdas for some k. And what we want to do is take any, just to explore what's going on, let's claim that any m lambda, for example, can be written as as a polynomial. If that is possible, then everything will be possible. So let's figure out how to write that. Okay, uh, in ek. Right. So here's the main idea. So if you're writing some polynomial such as this one in terms of EKs, okay, uh, first you start by finding the uh, leading term, the main term. So find the term with largest power of x1, and then among those pick the largest power of x2 and so on, and let's call this the main term. Of the polynomial. Okay, and we want so this is easy. For example, if you have m3 to 1, then the main term will be again, it's not writing very well. The main term will be x1 will be the highest, will be 3, then x2 square, then x3. So for example, this is also there, but this is lower than this one, so this is not allowed. So this term is also there in M3 to 3 to 1, but this is not the highest term. There's only one term in any polynomial, and that is what we are looking for. And we want to find a1, a2, an with the same main term. And let's say the main term is uh, x1 raised power b1, x2 raised power b2, xn raised power b. So what is e1, e2 up till so on? So this is x1 plus x2 plus so on up till xn, then x1, x2, then so on, and the last one is x1, x2, xn. So this is raised power a1, this is raised power a2, whatever, this is an. So how do we find the same main term as this guy? This is basically the main term of this. The main term of this is x1 to the a1 plus a2 plus an, right? Because you want the x1 to be maximum, so pick the term with x1 in all of them. Then once you've picked it up, you can't pick any this x2. So x2 will only come as a2 from this term plus a3 plus so on up till an, and so on. Xn will just have an. So how do we get the same term? So to get the same main term as this chap, we begin with so we take uh, an to be the same as bn, right? And an minus 1 you take to be uh, bn minus 1 minus bn, and an minus 2 you take bn minus 2 minus bn minus 1, and so on. Right, so for example, m that 3 to 1, let's say, um, and in this guy, in this chap, we are getting we take E3, then we take E2, and we take E1, and if we subtract that, we'll get rid of the main term. So the main term here will be x1 raised per 3, x2 raised per 2, and x3 raised per 1, and this one has the same main term. Right. So as long as this is a partition, one can do it. Right. So now consider.
So, Professor,
Yeah.
for the this term, how are we getting our relation? So we got x1 to the a1 to x1 to the power a1 plus 2 an, and then how are we getting x2 to the power a2 plus a3 and so on? Why don't we have an a1 term here?
Well, I mean, you want x1 to be the maximum term, so you have to take x1 from each guy.
Right,
So if you take x1 to the maximum here, you'll get x1 to the a1 from here, and x1 to the a2 here, and so on. Now, there's no option of taking x2 from here, because already I can only choose one guy, x1 raised per a1 here, right? All other terms have lower powers of x1.
right,
So I can choose, but here I can choose the same. I can choose x1, x2, so that x2 gets the maximum power amongst x3, x4. So I could have chosen x1, x3 as far as I want power of x1, but I would like x2 to have the highest power.
right. This makes sense. Thank you.
So that's why you go from 2 and so on. So, so now consider we started with this guy, let's say, and we consider E1, E8, E1, A1, E2, A2, E3, A3, and En, An. Now, the leading term here, the main term gets cancelled, and again, this is a symmetric function for sure. So again, take the guy with the leading term. So again, carry on this process. So this is a symmetric polynomial again, this chap right here, whatever it is, and it has again there will be some term involving the m's, which will be the leading term, and again follow this process. But the term which is there in the leading term, the new one will be smaller than, with the main term smaller in lexicographic order than the B1 Bn. So there are only finitely many uh, such functions, such partitions, B1, Bn, with the summation Bi equal to whatever we started with. Let's say we began with m lambda, right? So so then it will cover all, I mean, you keep going on, so this process will stop. So what you need to note is that this guy also is a homogeneous. Uh, every term is exactly the same main term. So if you sum up the b's, sum of the a's is the same as the sum of the b's, isn't it? So you'll get the same things actually. You'll get the same homogeneous term. So okay, let me do an example to make it clear what's happening. So let's try with M50 of x2. So this is the simplest one I want to do. This also takes some doing. So the main term is x1 to the 5, right? So what do I need? What will I do? I'll choose E1 basically. So I will choose E1 to the 5. So E1 to the 5 will be x1 plus x2 raised per 5. So M50 x2 minus E1 to the 5 So let's see, it's x1 raised power 5 plus x2 raised power 5 minus this whole thing. Uh, I just did it today in my calculus class. X, and I did it correctly there. So x1 cubed, x2 square plus, is there another 10 or just 5? X1 square, x2 cubed plus 5, x1, x2, 4 plus x2 to the 5. So I subtract this and I get um, minus 5x1 to the 4x2. This is the new dominant term. Minus 10, whatever I get. Okay, so now I add, what do I add? I add E2 and E1 raised per 3. So I add x1 plus x2 cubed into x1 x2. So which is x1 cubed plus 3x1 square x2 plus 3x1 x2 square plus x2 cubed into x1 x2. So I add this. What do I get? Um, well, so I add 5 times this to the previous guy, and I get M50 minus E15 plus 5 E1 cube E2, which will be equal to, so well, so let's see, let's go to different colors. So 5x1 cubed, x1 4, this one will cancel for sure with this guy. Then I'll get 3x1 cubed, 15x1 cubed, uh, x2 square. So this one, 15 minus 10, I will get 5 uh, x1 cubed, x2 square. So this term is taken care of. Then I get 15 x1 square, x cube cube, again same thing, plus 5 x1 square, x2 cubed. Then 5 times x2 raised to the power 4 x1, which is this guy. I'll cancel that. So this will get cancelled. And that's all I've got, right? So this is the main term now. What is the main term? Main term is this guy. So then I subtract with 5 times E2 square and E1. And this is minus 5 times x1 plus x2, x1 square, x2 square. And this will cancel the whole thing. x1 cubed, x2 square, and so this will be fine. So now I'll get so we get M50 minus E1 to the 5 plus 5 E1 cube E2 minus 5 E1 E2 square is equal to 0. So M50 is equal to this guy. Okay. So this is, I think, one of your homework problems. So this is an important point. I mean, this is the most important point of this lesson today. And anyway, back to the theorem. Um, what you do is for each um, n and k, you write down partitions, uh, lambda 1 bigger than lambda 2, so on. I mean, you pad enough zeros if you wish to make them whatever. Um, and order them. These are ordered lexicographically. So write the largest one first. So this lambda is equal to k. Let's fix the k. And you create this, and what you do is, uh, so let's say this is, I mean, for example, the first one would be k0. The second one would be, you know, there's 1 here, so there should be k minus 1 here. And so on. So you write all of them here. And here you write the corresponding partitions for ease. Okay. So in this first one, you will take e raised per k. In the second one, e1 raised per k. The second one, you'll take e2, then e1 raised per k minus 2, and so on. So write down all these corresponding partitions. And we are doing the reverse thing what we did earlier. Earlier we were writing m lambda in terms of this guy. So this is here. These rows represent m lambdas. Okay, the columns represent m lambdas with this lambda, and the rows represent whatever we are getting for ease. Okay, and then you write because m lambdas are a basis. You write these in terms of that basis. So you will get 1 here, and then you'll get some business here. You'll get 1 here and some business here, and 1 here and some business here, and so on. Right? So you'll get all these things. So you get this big matrix. So what am I doing here? I'm saying expand E A1 to E1 A1 to En An in terms of m lambda 1, m lambda 2, and so on, and write the coefficients in this matrix. Right? So if you write it, we just saw that, the diagonal entries would be 1 because the leading term of this guy is the leading term of this guy. Right? And all the rest are lexicographically smaller. Right? So we do that, and then what? Then my pad gets over. Then this matrix is invertible, right? I mean, this, you don't need a course in linear algebra to know that this matrix is invertible. Its determinant is 1. It is upper triangular. With determinant non-zero. Okay, say because it is whatever. So what? So invert. And write m lambda in terms of E1 raised power A1, right? This proves the theorem. Okay, so what are we doing? Uh, any questions? Have you got what we've done? I mean, it's a little bit meandering way of doing things, but anyway. So what we want to do is we want to write f any polynomial in this symmetric functions on n variables can be written uniquely as a polynomial. So first of all, we take, okay, let's restrict ourselves to polynomials which are homogeneous in degree k. Okay, so take any m lambda and I'll show you that it can be written in terms of a polynomial. I mean, the main important thing here in terms of m lambda is really that the leading term, the main term, is determinable by this kind of thing, this product of symmetric functions, right? And once you have that, then, I mean, this was just to go on to distraction to do your homework problem. Um, Once you do that, then you can write this matrix down. You can write all the lambdas in lexicographically decreasing order. So I hope you know what lexicographic ordering means. You know that, right?
Yes, Professor.
Okay. Um, so, so you write all of them
Basically,
in this order. Sorry?
dictionary ordering, basically, right?
Yeah. Lexico, I mean, lexicon is words, right? I mean, vocabulary. So
Right.
yeah, so it's a, I mean, the highest one is the one with the first guy, the next highest, and so on. So you look at the top guy. I think it's called reverse lexicographic because in the dictionary A comes before Z. I mean, it would have been much easier if Z came first. But anyway, I mean, there are less Z's, right? Anyway, so you write all these and then you write the corresponding E's as I showed you. You write this ordering is as per the corresponding uh, thing. So you write the partitions here in a different way, and then it's clear that the matrix is upper triangular with diagonal entries 1. And this is invertible, and so I mean it's a this in algebra this would be a one line proof, but in combinatorics one likes to see, okay, what is the matrix going to be? Can I calculate it? Can I do some examples? And in fact, nowadays in algebra also they do it. So if you're studying algebra from somebody who doesn't do this kind of calculation, then you should be doing it on your own. Otherwise, you're not learning anything. Anyway, so this proves this theorem, and let me define. I'll make some comments, further comments on this, but let me first define. Let lambda be equal to lambda 1, lambda 2, lambda n. Then E lambda I'll define as E lambda 1, E lambda 2, E lambda. So what we did over here, it's some partition. We are multiplying these two guys, and ek is just some number, the kth. So this is how one defines for a partition. And what have been shown, what we have shown is um, from the theorem, we see that E1 till En is a algebraic is a set of algebraic generators of lambda um, for uh, what does that mean? See, everything in here is a everything. So m lambda is a basis. So the vector space is generated by m lambda, right? And ek, they are algebraic generators. That means polynomials of ek generate the same thing. So right now it's generate, it's actually a basis. So it's actually a basis here, and one can argue this is also a basis very quickly. So let me argue that too. So E lambda, right, is also a vector space basis. Why is it a vector space basis? Well, spanning is clear. I mean, any polynomial in in E1 to EK, right, is you can write it as a linear combination actually of E lambdas. Okay. I don't know why. Let me move this around. Do you see that? Because if you have E1 raised per alpha 1, A1, E2 raised per A2, this is same as E of this lambda, A1, A2, A3. I mean, depending on, reorder it properly, whichever is the biggest. So it's a linear combination of some lambdas, and their number, how many are there?
PK.
So it's exactly pk, so it must be linearly independent, so this must be a basis. I mean, one of the two conditions have to hold, right? That it's a spanning set and it says so it must be linearly independent and therefore a basis. I mean, we are talking finite dimensional thing. So what does this mean? This means that this is dramatic. I mean, E1, E2, En are algebraically independent also. What does that mean? I mean, algebraic dependence is, for example, E is algebraically independent with rational numbers. So what that means is that there is no polynomial, no polynomial f y1 yn such that f of e1 en is equal to 0. Because if it was there, it would contradict the fact that E lambda are linearly independent. So any polynomial term can be basically written as E lambda, and then you take whatever the constant in front of it. So any polynomial will so it's algebraically independent, which means, what does it mean? Uh, Nothing. It means it's a different kind of uh, generating set than m lambda, and that's why it was useful. I mean, that this came up historically very quickly. I mean, things we are doing today are like known for centuries, basically. Anyway, so one thing one notes to, um, which I need to tell you, is this. So this is k minus 1. This is not k minus 1. This is n minus 1. Okay, xn e k minus 1. Well, either it contains xn or not. If it doesn't contain xn, it's over here.
So, Professor, the first term range is still xn minus 1? Yeah.
Yeah. It's looking like a elephant, right? So again, this is also true. We saw that. Well, it follows. So ek x1 to x n minus 1 and 0 will be ek x1 to xn minus 1. So if you put xn equal to 0, then you just get this guy. And this again, this means that you can look at an infinite set. I'll just remove this guy. So this is with an infinite set of variables. Okay, and since we've already done for m lambda, any f belonging to this guy, we've done it for a n large enough. So any f belonging to now with infinite set of variables is uniquely represented as a polynomial in. By the way, this uniquely business in polynomials is immediate because any polynomial has certain number of roots, and if there are two ways of writing the same thing, then it has you subtract the two, and you get a polynomial with a smaller degree, and so this linear independence business is very easy in polynomials. Let's say monic polynomials. If you know one, if you can just get rid of one term, reduce the degree, then you're home free. So that's a very interesting thing about polynomials. Um, okay, now I just want to make some remarks, for 5 minutes, very vague remarks about this infinite business. See, what is happening is you have a polynomial in x1, say, some symmetric polynomial in x1, and essentially the same polynomial in x2, but while coming back, you putting x2 equal to 0, you get this guy. But this is unique too. It's an isomorphism. So you have a sequence f1, f2, f3, and so on. So, and each of these guys is coming back when you put x3 equal to 0 and so on. So really, I would say really a symmetric function is a sequence of these f1, f2, f3, so on. And there's a, at some point when we saying that this at 0 comes back to this previous guy, there's a unique way of going from f3 to f2 also. So it's not that, f3 can go to two different animals, okay, in this sequence. It's an isomorphism type of thing, okay. So I'm deliberately vague because it involves some algebraic stuff which I don't want to get into. But understand that this is what is happening when we are saying that from some point on at 0, so it doesn't matter. If we are doing if we did some kind of a thing with over here, right? We did some calculation over here, right? And all the partitions involved were just two parts. So really, this same damn thing will work for three, n equal to 3, n equal to 4, n equal to 5. I just have to do it for n equal to 2. That's the whole point of this whole story. You see, because the partitions involved, the m lambda involved are just have these two parts, then I don't need more than, uh, I can just prove this identity and that's what it will work for everything. Now, you know, so for n large enough, n equal to 20,000 or some number, you can do the calculations without worrying about whether what you've got is correct or not. That's the whole point of this symmetric function business. So in the previous times, they used to just have one fixed variable and they would keep saying it's in 2 variables, 3 variables, 5 variables. Now we just say they should be in large enough set of variables. Okay, so that's elementary symmetric functions. There are two further um, sets, symmetric functions. Also polynomials. ek x1 to xn is defined as xi to the k, I going from 1 to n. This is called the power symmetric functions. And hk, this is the I1 x I2 x ik, and here I1 is allowed to be equal to I2. This is called the complete homogeneous symmetric polynomial or function. Okay, so what is the complete symmetric function? This is m lambda summed over all the partitions. So m lambda was one particular partition, and you took all its images, and here hk is you take all the hk is you take the sum over all of them. Okay. pk can also be written in terms of m lambda. It's this guy. So all the partitions are xn's are the same in both cases. Well, I won't write it. And ek is this partition with all ones. So here this lambda is this guy. All these things are k, and here the lambda is this term. Okay, and we have generating functions. Um, E of t, which is ek of t raised per k going from 0 to infinity. This is equal to 1 plus xit. So I going from 1 to either n or infinity, depending on whether you're doing infinite number of variables or not. So, well, this is a standard argument in generating in symmetric functions. Without loss of generality, we can assume n finite number of variables. So this guy 1 plus xit, I going from 1 to n. So this would be so you pick one guy from each I1, I2, I k. So there are if you pick k of them, then you will get t raised per k. Right. So this is obvious. With infinity, it's not so obvious, but without loss of generality, we can just take n, some n. And similarly, h of t is the generating function for 1 to n or infinity of 1 over 1 minus xi t. And we notice that 1 over 1 minus xi t, going from 1 to n, is equal to. So what you do is you expand each guy into um, power series. What should I say? Ki, I guess, right? And ki is going between 0, and here I is going from 1 to n. And then each of these terms, if you bring them together and you collate, so you get x1 to the k1, x2 to the k2, right? And xn to the kn, and you will have a t raised to the power k1 plus kn. So this is over all the possible ki's, right? Then collect together the coefficients of k, and you will get hk of these guys. If you collect together everything and collect all the ki's, then you will get k. And in both these cases, note that E0 is taken as H0 as well. Okay, any questions so far?
So, Professor, we are in the second line, we are summing over what are K's. K are the partitions.
No, I mean you take any random. So this is, take 3 from the first one, 4 from the second one from the third one, and so on. And you just multiply all these terms with each other, and you're summing over all possible such ki's, and then you collect, in this step you collect all the ki's which add up to k. So not really a partition, but a composition actually, everything which adds up to k, and then you get hk of xn. So you get all possible partitions and m lambdas and so on. Is that clear?
Yes, Professor.
So anyway, what does this mean? I mean, you take this guy and you take this guy. If you replace t by minus t, you get this guy, and in the denominator, so you get h of t equal to 1 over e of minus t. So now this is familiar territory for us. This is your Cauchy product. Let's take hk t raised per k going from 0 to infinity, multiplied by e to the k t raised per k with a minus 1 raised per k. And you multiply these two together, you get E0 H0 equal to 1, which is okay. I mean, we're taking E0 equal to 1 equal to H0. And then otherwise, we are getting um, Hn E0 plus Hn minus 1. I mean, you're taking powers of x to the n. So comparing powers of x to the n, you'll get H0 En equal to 0. So for n bigger than equal to 1, it's like a double. Yeah. So no, this is wrong. There is a minus sign here. So e's come with a minus sign. And so this is an infinite. This is an infinite set of equations, isn't it? So you get h1 in the first one, h1 minus e1 equal to 0. So you get h1 equal to e1. Then you get h2 equal to h1 e1 uh, minus e2, and h1 is e1, so it's e1 square minus e2, and so on. So you can calculate everything. So ek can be written in terms of hk, or rather hk can be written in terms and vice versa. So what does this imply? So it implies that hk's are also algebraic basis of sigma, right? Since ek can, I mean, since hk can be written in terms of ek, so you can replace whatever polynomials of e's are there, you can convert them into polynomials of h. So you get all of those, and further h lambda, which is defined as h lambda 1, h lambda 2, so on, are a vector space basis. So same argument, they generate, and they are p of n in number, p of k in number, so they have to. So what about pk? What can be? So is this clear? So homogeneous functions are very, very related. This is a bunch of equations. One can solve these equations, you know. In fact, that will be a good homework problem to give you to solve this set of equations. Um, and uh, they can be written in terms of each other. So let's try to write pk uh, in terms of these guys. So what is pt? That is summation pk t raised per k, k going from 0 to infinity. This is pk is very easy to write, right? I mean, it's x1 to the k plus x2 to the k and so on up till xn to the k. So this is 1 over 1 minus x1t plus 1 over 1 minus x2t plus so on up to 1 over 1 minus xnt, right? So you take log of 1 over the product of j equal to 1 to n, 1 minus xjt, and this will give you the sum of logs of these guys. Okay, and this is also something I did in my calculus class today, which are you sure you're there? Okay.
No, Professor, I wasn't there this morning.
Okay, so then you will not miss anything because I'm doing the same thing here. So what you do is you use this. We did this Taylor series expansion. So I mean, not worrying about convergence. This works for you know formal power series. So what we're going to get over here is that um, sorry, there's a minus sign here. If we get, I'll put this in a box so that I can put the equal to sign right here. So then I'll get j going from 1 to n, and then this whole thing, summation um, kj bigger than equal to 0, uh, xjt raised per kj over kj. Actually, why I need kj? I just need 1k. Because I already have the j here. So I just need a k. Each of these guys can be written as, uh, you know, just replace z by xjt, and this is what we get. And well, this is okay. You can interchange the guy again. K bigger than equal to 1, it should be. T raised to the power k over k, and this sum of xj raised per k is just pk. So what we've got is we've got log of ht uh, over here is equal to summation k going uh, and this strange kind of generating function. But anyway, you can calculate it. So this equation we can use star to calculate pk from hk. but I'm not sure whether you can do vice versa. Yeah, you can do vice versa. So, but it's a little bit, yeah. So you can use this. So you can do. What do I mean? I mean, for example, this is exponential of pk t raised per k over k, and this is you know 1 plus pk t raised per k over k raised per 1 plus pk t raised per k over k 2 1 over 2 factorial plus so on, right? And here you'll get some, and you can compare coefficients of t raised to the power whatever 0 1 2 from here.
So, Professor, exponential of the summation, right?
Yeah, exponential of the summation. So, but in any case, you can take these guys and you can, if you figure out how to take the coefficients, which we were talking about in the beginning of the course, to the right order, then you can just calculate values from here. So this is h1 plus h1t plus whatever. And vice versa, you can expand ht. ht is 1 plus something, uh, whatever. So you can expand this into a power series by the same thing and then compare the coefficients. So anyway, the moral of the story is that pk also generate uh, lambda algebraically. Okay, that's not bad. I've finished. Is that before time? Yeah. Okay, so any questions?